What's going on, everybody? It's Mr. Gustin back in the physics classroom. Today we are discussing the links and the similarities between linear kinematics and rotational or angular kinematics. We realized recently that there are a lot of connections between rotational physics and linear physics, and we're working to try to figure out the similarities so that we can help kind of bridge those gaps in our brains and use our understanding from first semester to help us understand second semester. And making those connections is incredibly important. So today, we're going to look at those connections right there. So on the board, what I currently have written out are our basic understandings of the three primary linear kinematic variables. It's displacement, that's velocity, and that's acceleration. So we have those written out. This is all old information that we should know over here, and we're going to try to draw connections across to rotational kinematics. Use the definitions we have over here and the variables and units and equations to try and make sense of what we have going on over here in rotational kinematics. So let's start with displacement. The most basic variable that we have is displacement, and it tells us how far and in which direction we are located from an initial point. So when it comes to angular displacement, it's not just displacement, now it's angular we're really discussing in terms of radians. That's our primary unit is the radian. And we're not talking about radians like in math class. It's the same idea, but we're not discussing it in terms of pi necessarily, right? Radians is just a different measurement for degrees. 360 degrees in a circle, and there are 6.28 radians in a circle. Most of you call that 2 pi, but sometimes it makes more sense to just use the actual number of radians as opposed to relying on that pi understanding. So those are just the same idea. Degrees and radians are very similar. They're just different ways of measuring the same thing. It's like Fahrenheit and Celsius. The same idea, different number systems. Okay? So angular displacement is measured in radians, and it tells us how far or how much something is rotated. Now, I'm a 90s baby, and so 90s babies, we all know Tony Hawk. And if you're a 90s baby that at all paid attention to skateboarding, what you know is that Tony Hawk became incredibly famous when he hit his famous 900. And the 900 was named because of the number of rotations he did. And so if I tell you someone moves 900 degrees, in your head you can think to yourself, well, 900 degrees would be 360 plus 360. You can figure out what that is. The 900 was a number of rotations. If you're a skateboarder from the 90s, you remember that there was a video game called 1080. 1080 was a trick pulled off by snowboarders that could get higher and move faster than skateboarders. 1080 was the number of degrees in a rotation. That was all just nerd speak for angular displacement. How that we literally have skateboard tricks and video games named after angular displacements. How much something has rotated in degrees, but we use here in physics, we use radians, okay? That's all angular displacement is, how much something has rotated and in which direction. The clockwise or counterclockwise direction. These are our directions. We don't move forward or backward. We don't rotate up or down. We rotate clockwise or counterclockwise about a pivot point. The next variable we have is our angular velocity. Not velocity, it's angular velocity. And angular velocity is denoted with the variable omega. It's a lowercase omega. It's kind of a flexy, squiggly W. That's what I think about when I see angular velocity. How is it measured? Well, it's measured, or it's calculated by taking my change in theta, or change in angle over time, and it's measured in radians per second. We don't use degrees so much. We prefer to use radians in physics, and so this is how we measure it. Which direction does it go? It's the direction that you are rotating. Whichever you are rotating. So if I'm rotating counterclockwise, my omega is counterclockwise. Lastly, The last variable we have is acceleration, or the rate of change of velocity. That's all angular acceleration is. It would be the rate of change of angular, and I'm going to abbreviate that, angular velocity. Its direction, well, if the acceleration is the direction of the net force, and I don't necessarily have forces causing rotation, torques cause rotation, well then the angular acceleration is going to be the same direction as the net torque. If the net torque is clockwise, my angular acceleration is clockwise. If the net torque is counterclockwise, then my angular acceleration is going to be also whatever I just said. I forgot what I said, clockwise or counterclockwise. They're in the same direction. I've got a synonym. I've got a comparison between acceleration and angular acceleration, and now I've got a comparison between net forces and net torques. They both point in the same direction as their respective acceleration values and vectors. These are the three basic variables in kinematics that appear in our basic equations for kinematics. So when I think about the equations that are useful for me rotationally, all I need to do is transcribe these equations over using their respective variables. For example, this first equation is final velocity is equal to initial velocity plus the acceleration times time. This is a reasonable rotational or angular kinematic equation. I've simply replaced my linear variables with my angular variables, and I have a new equation. Let's try it again. For our displacement one, I see angular position equals initial angular position plus initial angular velocity times time plus 1/2 angular acceleration times time squared. I've just simply replaced the variables in linear kinematics with my variables from rotational kinematics. It's very straightforward. These are mathematical relationships that still hold true. Lastly, we would say there's a angular velocity squared equals initial angular velocity squared plus 2 alpha change in theta. This equation also holds true. Now, these equations work independently of each other. These equations might discuss an object moving on a line, an object in free fall. Over here, these things might discuss objects that are in simply rotating around a pivot. The weird thing is that sometimes I get both motions combined. I get something that is rotating and moving across the floor simultaneously, almost as if the rolling or rotating is causing the linear motion. If both things are taking place, I've got some unique mathematical relationships. Again, let me say that again. If something is rotating and that rotation causes linear motion, there is definitely a way, there's some cool and interesting relationships between the two directions that I can rely on to study the motion kinematically. Let's go ahead and look at an example of what I'm talking about over here. Okay, I'm going to go ahead and grab the tire from yesterday, and we'll see what I'm talking about, because tires are a great example of objects that roll and cause things to move linearly. It's literally how vehicles work. Bikes, cars, trucks, anything with wheels, it's how they work. So let me show you an example of what I'm talking about. If this tire on the ground moves across the floor, or as it moves across the floor rather, the rolling motion of the tire creates linear motion. So you get what I'm saying? Like, because it rolls, it also moves forward. And when we have that kind of motion, I give it a name. I call it bridgeable motion because there's bridging. I'm allowed to kind of connect the two directions between linear and rotational. So when this happens, let's think about this. I'm going to think about a question I asked you a couple days ago, right? A couple days ago I said, if this thing rotates once, how far has it traveled? Let's draw a picture of that. If it rotates once, one complete rotation around its axis of rotation, it's rolled once, how far has it traveled? And most of you said, Gustin, that's easy. If it rolls once, that's just the circumference. You're basically saying the distance that it's traveled is equal to 2 pi times r. And I say, great. That's not earth-shattering. I haven't taught you anything. You knew that before you came to physics. But what I'm not sure you did know is that 2 pi is actually the angular displacement of the tire, right? How many rotations? 1 rotation, 360 degrees. If you know your unit circle, that's 2 pi radians. Technically speaking, what we just did was to find our linear displacement, we took the angular displacement and multiplied it by its radius. This is a connecting equation. This is what I call a bridge equation. A bridge equation is an equation that allows me to take my linear variables and relate them to rotational motion. So, if I want to figure out how far something has traveled linearly, I need to first figure out, well, what angle has it swept out and what's the radius? And if I know the angle it has swept out and how big the radius is, I can figure out how far it's moved linearly. For example, what about this tire only making half a rotation? Let's say I started down here with the screw down and it goes half a rotation. Boom, half of a rotation. I wonder how far it traveled. Well, it's not a circumference, it'd be half a circumference. So if it's half a circumference, it's now the thing. What if it's a third of a rotation? These things get weird. But if I know that half a rotation is 180 degrees or 3.14 radians, all I have to do is take that value, plug it into my equation, measure the radius, and I know exactly how far it's traveled linearly. This is an equation that works. Now, from this first equation, if I think about it, all I have to do is a little bit of algebra. Instead, what if I don't want to know how far it's traveled? What if I only know how fast it's traveling? How quickly an object is moving across the room or down the road? If that's true, I know this. Quickness or speed is distance over time or displacement over time. This equation stays the same. If I divide this side by time, and then algebraically to keep the equation the same, I also divide this side by time to keep the equation the same. What I end up with is velocity, and what I end up with is omega and r. My second equation, if I know how fast something is moving, either angularly or linearly, and those motions are happening because of one another. The rolling is causing the linear motion. If this is the case, I have a second bridge equation. I can use the speed of an object linearly to relate to its angular velocity. If it's moving at a certain pace, I can figure out how quickly that angle is moving if I know the radius. And likewise, I have one more. In keeping with this tradition, I can say alpha, or the acceleration of an object, its linear acceleration, is also equal to the angular acceleration times r. And again, that's for the same algebraic reasons we had before. I want to remind you, and it is so important that you are clear on these 3 bridge equations. These equations only work if the rotating motion is causing the linear motion. Basically, if I took this tire, picked it up, and just rotated it around like this, it's rotating, but it's not moving linearly. So no, I wouldn't have any linear motion because of that rotation. But if the tire's rolling is causing it to move, I can rely on those bridge equations to connect me into these equations or to convert between variables so I can go ahead and calculate whatever it is I'm looking for. Distance, velocity, acceleration, net force, who knows? But I need to make sure that motion is what I call bridgeable. And if it is, we have these unlocking 3 equations. Okay? These are the connections between linear and rotational kinematics and the rare case, the unique case, the cool case, where I can actually use mathematics to bridge between the 2 directions, the 2 types of motion when things roll without slipping. If you got questions in the comments, send me an email. Ask me in class. Until next time, see ya!